episode number 65 of the Piezo Shock Show. I'll describe a parameter that you can use when optimizing your ultrasonic transducer using modal analysis. I described this in my webinar, so you can search for that in some of my recent videos. But here I'm going to give I had a question about, well, should we, how do we properly understand tip displacement versus crystal stretch? So I described in that webinar, if the ratio between how much the crystal expands and the tip of the transducer, and then I'm showing in a common kind of mode-shaped diagram. Here's the tip of the transducer, and here's the crystal stretch. So I assume that the crystal starts and ends here, those rings, and this displacement in this direction is basically how much they've actually expanded from their original positions compared to the how do we understand tip displacement versus total crystal length increase to be something you want to optimize? And one question is, wouldn't we want to increase the amount that the crystal is stretching? Wouldn't we want that to be more, in order for our transducer to improve and be better? The actual answer is that no, we're not trying to necessarily, per volt. All right, we're going to tell you something else. So per volt, would we want our crystals to expand more? And that would mean they are better coupled to our transducer. However, in modal analysis, we're not doing things per volt. We're doing things as a ratio of elastic behavior. So this is a purely elastic domain. So don't think per volt. Think that the crystal stretch, or the crystal, you could call it crystal stress. Now it's a little bit more complicated to calculate, maybe take some integrations, but the amount that the crystal stretches in the finite element simulation is actually going to be very, it's going to be proportional to the amount of stress generated in the crystal, which is basically what the crystal does when you apply voltage under a condition where there's resistance. It produces stress inside of it, which then allows the accumulation of that then creates force and creates the oscillation force, which then travels down the horn and creates our resonant structure. So if we have more tip displacement for a smaller change, that means we can use less voltage. So crystal stretch could also be an analog to voltage. So minimizing voltage and maximizing tip displacement is another way to look at this. So this is an important it's an important concept here, and definitely a way to, in modal analysis, like typically somebody may only think to improve their modal analysis by putting their crystals at the horn, their crystals at the nodal point. But you can there's actually two other things you can do and calculate to optimize your transducer. The first is optimizing tip displacement versus crystal stretch, or you can do strain by dividing by the length. That's fine too, because it's just about the same thing. You can also calculate the electromechanical coupling factor, which I described in the webinar I did a few days ago. And that webinar was called, I don't remember the name of it, but it was, I think, using modal analysis like an expert. If you search that up on Google or on YouTube with Learn Piezo, you'll end up at the video. All right, so thanks for watching this, and I will see you in the next episode. And be sure to check out the link in the descriptions for understanding more about my consulting services in the area of ultrasonic transducer development.